Here are two numbers, 67 and 73. They are two measurements of the same thing, how fast the universe is expanding right now, made by two teams using the finest instruments our species has ever built. They are supposed to be the same number. They are not. And here is the part that should stop you. As the measurements got sharper, the two numbers did not move closer together. They drifted further apart. The Big Bang is the most successful theory in the history of science. It predicts the temperature of the infant universe to better than 1 part in 1,000. And yet the closer we look at it, the more it refuses to agree with itself, about its own expansion, about what 95% of it is made of, about the very moment it began. So what is actually going on? Why does the best theory we have make less sense the more carefully we study it? Get comfortable. Hit subscribe if you're new here, because by the end of tonight, you will understand exactly what it means when a theory this good starts to come apart at the edges, and why that might be the most hopeful thing happening in physics. Now, let's slowly ease into this. Part 1. The most successful theory we have. Let me begin by telling you something that will make everything else in this video stranger, and it is this. The theory we are about to slowly take apart, the theory that seems to fall further out of focus every time we look at it more closely, is not a bad theory. It is not a shaky theory. It is, by almost any measure you could name, the single most successful description of the universe that human beings have ever written down. So before we go anywhere near the cracks, I want you to feel how solid the ground is, because the whole strangeness of tonight depends on it. The idea is simple enough to say in one breath. The universe was once hot and dense and much smaller than it is now, and for something like 13.8 billion years, it has been expanding and cooling into the vast, cold, quiet thing we live inside tonight. That is the Big Bang. Not an explosion, not a bang, not really, though we will come back to that. Just a universe that used to be small and hot, and has been growing and cooling ever since. And from that one idea, physicists built a model. They gave it a slightly clumsy name, lambda CDM, which stands for a cosmological constant plus cold dark matter, and we will meet both of those characters later, because both of them are trouble. But here is the thing about this model that you need to hold on to. It runs on only 6 numbers. 6. You feed in 6 values, 6 parameters measured from the sky, and out of those 6 numbers, the model reproduces an astonishing sweep of everything we see. It predicts how fast the universe is expanding. It predicts the exact recipe of the lightest chemical elements, how much hydrogen, how much helium, how much of a trace of lithium was cooked in the first few minutes of time, before there were any stars to cook anything. And most impressive of all, it predicts the faint pattern of warmth and coolness printed across the oldest light in the sky, the light we call the cosmic microwave background, and it matches that pattern to a precision better than 1 part in 1,000. Think about what that means for a moment. A theory, built from 6 numbers, tells you what the temperature of the entire sky should look like when the universe was less than 400,000 years old, and then you point a satellite at the sky, and the sky agrees, decimal place after decimal place. That is not luck. That is not hand-waving. That is one of the great intellectual achievements of our species, and no serious scientist anywhere doubts the core of it. The universe really was hot and dense. It really has been expanding. This is as settled as the fact that the Earth goes around the Sun. Let me give you just a little more of the recipe, so the size of the achievement really lands. In the first few minutes after the beginning, when the whole universe was hotter than the center of a star, the lightest atomic nuclei were forged. The model predicts that this early cooking should have left the universe about 3/4 hydrogen and about 1/4 helium by mass, with just a faint trace of a couple of other light elements mixed in. And when we go out and measure the oldest, most pristine gas we can find, gas that has never been through a star, that is almost exactly what we see. 3 parts hydrogen to 1 part helium, matched to within a percent or two. The theory reached back to the first 3 minutes of time, told us what elements should exist, and the universe agreed. And the microwave background does something even more remarkable than simply matching. Its pattern of warm and cool spots has a series of peaks, a kind of cosmic sheet music, and the exact heights of those peaks encode how much ordinary matter and how much dark matter the early universe contained. Physicists predicted the shape of those peaks before the best measurements came in, and when the measurements arrived, the peaks stood exactly where the theory said they would. The third peak, in particular, is a direct fingerprint of dark matter, printed into light, that is nearly 14 billion years old. When a theory predicts something that specific, that far in advance, and the universe delivers it, you have earned the right to trust that theory deeply. This is not a house of cards. This is a cathedral, and that is exactly why the cracks, when we find them, are so unsettling. You do not worry about cracks in a shack. You worry about cracks in a cathedral. So keep that feeling close, the feeling of standing on something firm, because I am about to start tilting the floor. Here is the quiet paradox that this whole video lives inside. Over the last 15 years or so, and with a particular sharpness since around 2019, something odd has been happening to this beautiful, successful theory. As our instruments got better, as our telescopes got larger, and our surveys got deeper, and our measurements got more precise, the theory did not get more comfortable. It got less comfortable. The numbers started to disagree with each other. Not wildly, not everywhere, but in specific, stubborn, sharpening ways that refuse to go away. The most basic quantity in all of cosmology, the rate at which the universe is expanding right now, has split into 2 different answers depending on how you measure it, and the gap between those 2 answers has grown into what physicists now openly call a crisis. 95% of everything the universe contains has turned out to be 2 substances that nobody has ever directly detected, that we know about only because we can feel their gravity. And just in the last couple of years, the largest map of the cosmos ever made has begun whispering that one of those substances, the one we assumed was a fixed and unchanging feature of empty space, might actually be changing over time. That is the paradox. The Big Bang works better than almost any theory ever devised by anyone, and the closer we look at it, the less internally consistent it becomes. The better our eyes, the stranger the picture. And tonight we are going to walk through that strangeness, slowly and carefully, one crack at a time, until we understand what it might actually mean. Because the answer, when we get to it, is not what most people assume. It is stranger and quieter, and in a way, more hopeful than either the people who say the Big Bang is a lie, or the people who say it is finished and perfect. So settle in with me. We are going to start not with a crack, but with the deepest one of all, the one hiding at the very beginning, at the moment the theory is actually named after. Because it turns out the Big Bang has a problem right at the instant of the Big Bang, and it is a problem the theory can never solve on its own. Part 2. The one frame. The film cannot show. I want you to imagine that the entire history of the universe is a film, and we are going to run it backward. Right now the film shows what we see tonight. Galaxies scattered across the dark, drifting apart from one another. The whole thing slowly expanding, slowly cooling. Now we start to rewind. As we do, the galaxies begin sliding back toward each other. The space between them shrinks. The universe grows smaller, and because you cannot squeeze a universe without heating it, it also grows hotter. Keep rewinding. The galaxies dissolve back into formless glowing gas. The gas grows denser and brighter, until the whole cosmos is a single, uniform white glare, hotter than the core of any star, a fog of pure radiation so thick that light itself cannot travel through it. Keep winding the film back. The seconds compress. We pass the moment when the first atomic nuclei formed. We pass into the first second, when the universe was a searing soup of fundamental particles. The temperature climbs past anything that matter as we know it could survive. And the equations, Einstein's equations of general relativity, the same equations that have guided us flawlessly all the way down, keep telling us the story, smaller and hotter, right up until the very last frame. And then, at that final frame, the film tears. Because when you reach the instant we call the beginning, the mathematics does not give you a very small, very hot universe. It gives you something that is not a physical answer at all. It gives you zero size, infinite density, infinite temperature, infinite curvature of space and time. Every quantity that should be a number becomes infinite, all at once. Physicists have a name for this. They call it a singularity. And a singularity is not a thing. It is not a place. It is the sound a theory makes when it breaks. Infinity, in physics, is almost never a real measurement of the world. When your equations start handing you infinities, they are not describing something infinite. They are telling you, in the only language they have, that they have stopped working. It is the mathematical equivalent of dividing by zero. Your calculator does not show you the true answer to 1 divided by 0. It shows you an error, because the question itself has fallen outside what the arithmetic can handle. And that is exactly what general relativity does at the first moment of time. It throws an error. The theory that describes the expanding universe so beautifully, so precisely, cannot describe the one instant it is named after. Let me sit with you in the strangeness of that for a second, because it is easy to rush past. We have a theory of the origin of everything, and that theory cannot describe the origin. The map of the universe has a hole burned right through it, and the hole is located exactly where the story is supposed to start. Now, you might reasonably ask, is this just a quirk? Maybe if we had cleaner equations, or made better assumptions, the singularity would smooth itself away. And this is where it gets worse, not better. In the 1960s, two physicists, Roger Penrose and Stephen Hawking, proved a series of theorems, mathematical proofs, showing that under general relativity and some very mild, very reasonable assumptions about how matter behaves, this singularity, in the cosmic past, is essentially unavoidable. It is not a mistake in the setup. It is not something you can dodge with a cleverer model. It is baked into the theory itself. If general relativity is correct all the way back, then the beginning must be a place where general relativity fails. The theory, taken to its logical end, proves its own breaking point. It is worth pausing on how unusual that is, because most theories do not politely announce their own limits. They just quietly give wrong answers, and you have to catch them at it. General relativity does something rarer and, in a way, more honest. It tells you, in its own mathematics, precisely where it can no longer be trusted. It is like a map that, instead of simply going blank at the edge of the known world, has words printed at the border that read, "Beyond this line, this map is meaningless." That is a strange and almost noble thing for a theory to do. It hands you a warning along with its failure. And there is a subtlety here that is easy to miss, so let me make it explicit. The singularity is not necessarily a real, physical thing that actually existed. Most physicists do not believe there truly was a moment of infinite density. Rather, the singularity is a sign that our description has run out, that the true physics of that moment is governed by rules we do not yet possess. Think of it like this. If you are navigating with a flat map of the Earth and you sail off the top edge, the map might tell you that you have reached a place of infinite strangeness, an impossible boundary. But there is no such boundary on the actual globe. You have simply reached the North Pole, a perfectly ordinary place where your particular flat map happens to break down. The infinity was in the map, not in the world. The singularity at the beginning of time may be exactly that kind of illusion, a place where our flat map of physics tears, while the real territory, whatever it is, remains smooth and lawful and simply beyond our current sight. The trouble is that we do not yet have the globe. We only have the torn map, and the tear sits precisely where the story is supposed to begin. So what is actually there, at that first instant? The honest answer is that we do not know, and we cannot know, not with the physics we currently have. To describe that moment, we would need a theory that combines general relativity, which governs the very large, with quantum mechanics, which governs the very small. At the singularity, the entire universe is both unimaginably heavy and unimaginably tiny, so both sets of rules apply at once. And right now, we have no working theory of quantum gravity that can handle that. There are candidates. There are ideas where the singularity is replaced by a bounce, or by some finite, gentle transition instead of an infinite spike. But not one of them is confirmed. Every one of them is a sketch in the margins of a page we cannot yet read. Let me give you a taste of just how different those sketches are from one another, because it tells you how open this question really is. In one family of ideas, called bouncing cosmologies, there was no true beginning at all. Instead, a previous universe collapsed inward, growing denser and hotter, until, just before it would have hit the singularity, some quantum effect halted the collapse and flung it back outward. What we call the Big Bang, in that picture, is really the Big Bounce, the rebound of an earlier cosmos, and time extends backward past it into a whole prior history. In another family of ideas, the beginning is a smooth, rounded thing with no sharp edge, the way the surface of a globe has no edge even though it is finite, so that asking what came before the beginning becomes as meaningless as asking what lies north of the North Pole. In still others, our universe is one bubble that formed in a vast, eternally inflating background, and its beginning was simply the moment that bubble nucleated, with an endless landscape of other universes stretching away on every side. These are not idle daydreams. They are serious mathematical proposals by serious physicists. And the striking thing is that they cannot all be right, yet each is compatible with everything we currently observe. That is the honest situation. We have several radically different stories about the deepest question there is, the origin of everything, and no way, yet, to tell which one, if any, is true. And notice what that means about the phrase we keep returning to. It is not just that the Big Bang makes less sense the more we study it. It is that at the very deepest level, the level of the beginning itself, we do not even have one story we are trying to confirm. We have a shelf of competing stories, and an empty space where the evidence should be. The beginning of the universe is not a solved problem with a few loose ends. It is an open frontier, as wide open now as it has ever been, and everything we build on top of it inherits that openness. And here is the human weight of it. When someone asks you what banged in the Big Bang, or what came before it, the deepest honest answer is that the theory does not contain that moment. The beginning, as the popular story tells it, is precisely the one place our best theory of the beginning goes dark. We have not lost the first frame of the film. It was never in the reel to begin with. So already, before we have touched a single new discovery, before we have looked through a single modern telescope, the Big Bang has a hole at its very center. And we are only getting started, because the next problem is not a hole in the theory. It is something that everyone thinks they understand about the Big Bang, and almost everyone has completely wrong. Part 3. The thing you were taught was wrong. There is a picture almost everyone carries in their head when they hear the words Big Bang. It is a picture of a tiny, brilliant point sitting alone in a great empty darkness, and then, suddenly, it detonates. A cosmic explosion, throwing matter outward in all directions, filling up the empty space around it with stars and galaxies. It is a vivid picture, it is a dramatic picture, and it is wrong in almost every detail that matters. Let me take the pieces apart one at a time, gently, because getting this right is the difference between understanding the rest of tonight and being quietly lost. First, the Big Bang was not an explosion in space. It was an expansion of space itself. This is a genuinely difficult idea, so let me give you the image physicists use. Imagine the surface of a balloon, and imagine you have drawn dots all over it with a marker. Each dot is a galaxy. Now you blow the balloon up. Every dot moves away from every other dot. Not because the dots are traveling across the rubber, but because the rubber itself is stretching, carrying the dots along with it. There is no dot at the center of the expansion. There is no special dot from which all the others are fleeing. Every dot sees every other dot moving away. The expansion is happening everywhere, all at once, to the fabric itself. That is what the universe is doing. Galaxies are not flying outward through space, away from some central explosion. Space itself is stretching, and the galaxies are simply carried along on it, like the dots on the balloon. And this is why the question people always ask, where did the Big Bang happen, has no answer. It did not happen at a point. It happened everywhere. The place where the Big Bang occurred is the place you are sitting right now, and also the most distant galaxy, and every point in between, all at once. There is no center, because there is no outside for a center to be measured against. Second, and this follows directly, there is no edge and no outside. The universe is not an expanding ball of galaxies sitting inside a larger empty room. As far as we can tell, there is no room. The expansion is not the universe growing into some pre-existing emptiness. It is the emptiness itself, the space itself, that is growing. There is nothing for it to grow into. I know how strange that is to hold in your mind. Take your time with it. The stretching is not happening inside space. The stretching is happening to space. And third, here is the one that connects back to where we just were. The standard Big Bang theory does not actually describe the first instant at all. It describes the aftermath. It picks up the story a tiny fraction of a second after the beginning, when the universe is already hot and dense and expanding, and it follows the story forward from there with breathtaking accuracy. But that mathematical instant of zero size and infinite density, the singularity we just spent so long inside, the theory does not reach it. So when we say the Big Bang, what the science actually describes is not a creation event. It is everything that happened after a beginning it cannot see. Now let me tell you where the name itself came from, because it is a small, almost comic piece of history that has been quietly misleading people for 70 years. In the middle of the 20th century, there was a real scientific fight about the origin of the universe. On one side were the people who thought the universe had a hot, dense beginning. On the other side was an astronomer named Fred Hoyle, a brilliant and stubborn man who believed the universe had always existed, roughly the same, forever, with no beginning at all. Hoyle thought the idea of a sudden origin was faintly ridiculous, and in 1949, giving a talk on BBC radio, he reached for a dismissive phrase to make the idea sound crude and silly. He called it, with a sneer, this Big Bang idea. He meant it as an insult. He was mocking it, and the name stuck. It stuck so well that today, every child learns it, and every one of them pictures exactly the crude detonation that Hoyle was making fun of, the very picture that the theory says is wrong. The most famous name in cosmology was coined by the theory's biggest opponent as a put-down, and it has been shaping how the public imagines the universe ever since. There is a small irony worth savoring here. Hoyle was, by any measure, a great scientist. He did foundational work on how the elements heavier than helium are forged inside stars, work so important that it underlies much of modern astrophysics. He simply happened to be wrong about the beginning, and in his wrongness, he handed the winning side its most enduring brand. The man who thought the universe never began gave us the name we use for its beginning, and the name he chose to belittle the idea has done more to spread a misunderstanding of it than any deliberate campaign ever could have, because those two little words, big and bang, plant the wrong image in the mind before a single fact can be explained. I dwell on this because language shapes intuition more than we admit, and a bad name is a kind of quiet, permanent misinformation. If the theory had been called, say, the Great Expansion or the Everywhere Stretching, generations of people would carry a truer picture in their heads. They would not ask where it happened, because expansion does not happen at a place. They would not imagine an edge, or an outside, or debris flying through the dark. The whole tangle of misconceptions we just spent this part unknotting flows, in large part, from a phrase invented as a joke on the radio in 1949. So when we go looking, in the rest of this video, for the places where the Big Bang seems not to make sense, keep one thing in the back of your mind. Some of the not making sense was never in the universe at all. It was in the words we chose. But not all of it. Most of it, as you are about to see, is real, and it is written into the sky itself. I am telling you all of this for a reason that goes beyond trivia. When people say, as more and more of them do, that the Big Bang makes less and less sense the more we study it, you need to understand what part they are talking about, and what part they are not. They are almost never talking about the core claim, that the universe was once hot and dense and has been expanding. That claim is rock solid. It is not in danger. What is cracking, what is genuinely, deeply in trouble, is the precise version of the theory. The version that tries to nail down every number, every ingredient, every detail of how the universe grew from that hot, dense state into the one we see. That version keeps failing its own tests. And now that you know which part is bedrock and which part is trembling, we can go and look at the trembling, starting with a piece of the sky that agrees with itself for absolutely no reason at all. Part 4. The sky that agrees for no reason. I want to take you to the two most distant places you could ever look, and show you something about them that should not be possible. Point a telescope at one edge of the observable universe, as far as light has had time to travel to us, more than 13 billion light-years away. Note what you see, the faint glow of the early universe, and measure its temperature. Now turn your telescope around, a full 180 degrees, and look at the opposite edge of the observable universe, the same enormous distance away in the other direction. Measure its temperature too. The two temperatures are the same, not roughly the same to about 1 part in 100,000. If you measured the warmth of those two utterly separate patches of sky, on opposite sides of everything, you would find they agree down to the 5th decimal place. And now let me tell you why that is a genuine problem, one that kept cosmologists awake for decades. Those two regions of the sky have never been in contact, ever. Not once in the entire history of the universe. Light, the fastest thing there is, the thing that sets the absolute speed limit on any signal, any influence, any exchange of heat whatsoever, has never had time to travel from one of those regions to the other. They are, in the language of physics, outside each other's horizons. Each one sits beyond the farthest distance the other could ever have reached, even at the speed of light, even given all the time since the beginning. Think about what it takes for two things to have the same temperature. A hot cup of coffee and a cold room reach the same temperature because they are in contact, because heat flows between them until they settle into balance. Two regions of anything come to match because, at some point, they could talk to each other, could trade energy until they evened out. But these two patches of sky never could. They have never exchanged so much as a single photon. There is no mechanism in the standard picture by which they could have agreed on a temperature. And yet they agree, everywhere, in every direction, to a staggering precision. The entire sky, all of it, patches that have never met, share the same temperature as if they had all quietly conferred beforehand and settled on a number. This is called the horizon problem, and I want you to feel how deep it goes, because it is not a small technical footnote. It is asking why the universe is so uniform, so smooth, so agreed upon, when nothing in the theory allows for the conversation that would have produced that agreement. It is as if you walked into a stadium full of strangers who had never met, never communicated, never been in the same room, and found that every single one of them had, independently, chosen to wear exactly the same shade of a color, mixed to 1 part in 100,000. You would not say, "What a coincidence." You would say, "Something is going on here that I do not understand. Something must have connected them that I cannot see." That is exactly the position cosmologists found themselves in. The uniformity of the universe is not a comfort. It is a puzzle. A smooth, even, agreed-upon cosmos is far harder to explain than a lumpy, random one would have been, because smoothness implies communication, and the communication was impossible. Let me make the impossibility as concrete as I can, because it is the crux of the whole problem. Light sets the ultimate speed limit. Nothing, no signal, no ripple, no whisper of influence can travel faster than light. So the farthest any effect could have reached, since the beginning of time, is the distance light could have crossed in that time. That distance defines what we call a horizon, a bubble around every point, beyond which nothing could yet have touched it. And when we do the arithmetic for the early universe, we find that at the moment the microwave background was released, the horizon around any given patch of sky was tiny, far smaller than the sky we now see. The universe we observe today is stitched together from a huge number of these little patches, thousands of them, each one of which was, at that early time, completely sealed off from the others. No two distant patches had ever been inside each other's horizons. No heat had ever flowed between them. By every rule we know, they should have cooled to whatever random temperatures they happened to start with, and the sky should be a chaotic quilt of hot and cold regions with no reason to match. Instead, it is smooth, uniform, agreed. And so cosmologists were left holding a genuinely disturbing conclusion. Either an astronomical number of causally disconnected regions all independently, by pure chance, arrived at the identical temperature, which is absurd, or something happened in the very early universe that we were not accounting for, something that let those regions communicate after all, or share a common origin, before they were flung apart. The uniformity was not a detail to be filed away. It was a scream for new physics, and the flatness sitting beside it only made the scream louder. And there is a companion problem sitting right beside it, just as strange, called the flatness problem. When we measure the overall geometry of the universe, whether space on the largest scales is curved like the surface of a sphere, or curved the other way like a saddle, or perfectly flat, we find that it is flat, extraordinarily, almost perfectly flat. And that turns out to be its own kind of miracle, because flatness is unstable. If the early universe had been even slightly curved, that curvature would have grown enormously over billions of years, the way a tiny error at the start of a long journey lands you in a completely different country. For the universe to be as flat as we see it now, it must have started out flat to a precision of something like 1 part in 10 to the 62nd power. That is a 1 followed by 62 zeros. The early universe had to be balanced on a knife edge so fine that no one could explain why. So here we are. The universe is too smooth and too flat, and nothing in the basic Big Bang model tells us why it should be either. These are not small discrepancies. They are enormous, glaring features of everything we see, and the theory, on its own, simply cannot account for them. Now, physicists did find a possible answer to both of these problems at once. It is a beautiful answer, an elegant answer, and it has become part of the standard story. But here is the twist that sets up everything to come. The answer they found is itself one of the strangest and most contested ideas in all of physics. In solving the mystery of the smooth, flat universe, they may have simply traded it for a deeper mystery. And that is where we go next. Part 5. The patch that became its own mystery. In the late 1970s and early 1980s, a young physicist named Alan Guth was wrestling with exactly the problems we just walked through: the smoothness, the flatness, and a third one involving certain exotic particles that the early universe should have produced in vast numbers, but which we never find. And he arrived at an idea so powerful that it solved all three in a single stroke. The idea is called inflation. Here is the picture. Inflation says that in the very first tiny fraction of a second of the universe's existence, far less than a billionth of a billionth of a billionth of a second, the universe underwent a burst of expansion, so violent, so explosive, that it doubled in size, and doubled again, and again, dozens of times over, growing by a factor so large it is almost meaningless to write down. A patch of space smaller than a single proton was stretched, in that unimaginably brief instant, to something larger than the entire observable universe today. And watch how neatly this solves our problems. The smoothness? Before inflation, the whole observable universe was a tiny region, small enough that every part of it was in contact, could exchange heat, could settle into a common temperature. Then inflation took that already agreed upon patch and blew it up to cosmic size, preserving its uniformity as it stretched. The two opposite edges of the sky match because, before inflation, they were right next to each other, close enough to talk. Inflation just carried them enormously far apart, while keeping the agreement they had already reached. The flatness: take any curved surface and stretch it by a factor that large, and it becomes indistinguishable from flat, the same way the ground beneath your feet looks flat, because the earth is so much larger than you. Inflation flattens the universe simply by making it vast. And that third problem, the missing exotic particles? Certain theories predict that the hot early universe should have produced enormous numbers of heavy, stable oddities called magnetic monopoles, and yet we have never found a single one. Inflation explains their absence effortlessly. If they were made before the Great Stretching, then that stretching diluted them so severely, spreading them across such an unimaginably larger volume, that there would be at most a mere handful in the entire observable universe today, far too few for us to ever stumble across. One idea, three deep problems, solved at a stroke. You can see why it was irresistible. It is a gorgeous idea. It solves the horizon problem, the flatness problem, and the missing particle problem all together, and it made further predictions about the tiny ripples in the early universe that later observations appeared to confirm. For these reasons, inflation became part of the standard model of cosmology, widely taught, widely accepted. On the surface, this looks like a triumph, a case where the theory faced a crisis and physics rose to meet it. But now let me turn the idea over and show you its underside, because this is where the trouble lives. First, nobody knows what caused inflation. For this incredible burst of expansion to happen, there had to be something driving it, some field, some form of energy with very particular properties, filling the early universe. Physicists gave it a name, the inflaton, but naming it is not the same as finding it. We have never detected this field. We do not know what it was, where it came from, or why it had exactly the properties needed to make inflation work. The mechanism that solves our mysteries is itself a complete mystery. Second, and this is stranger, in most versions of the theory, inflation does not cleanly stop. Once it begins, quantum effects keep it going, in some regions even as it ends in others, so that inflation never fully switches off across the whole of reality. It keeps going, forever, spawning pocket after pocket, bubble after bubble, each one a separate universe, with potentially different properties. This is called eternal inflation, and it implies not one universe but an endless, ever-multiplying multitude of them, a multiverse. Our entire cosmos, everything we can see, becomes just one bubble among infinitely many. The theory we invoked to explain our tidy, uniform universe ends up predicting an uncountable infinity of universes we can never observe. And third, the deepest cut of all, and it comes from inside the field itself. One of the original architects of inflation, Paul Steinhardt, a man who helped build the theory, became one of its most forceful critics. His argument is devastating in its simplicity. He points out that inflation, in its full form, is so flexible that it can be tuned to produce almost any outcome you like. Different versions, different starting conditions, different values of that mysterious field, and you can get a universe with almost any properties. But a theory that can predict anything, Steinhardt argues, predicts nothing. If every possible observation is compatible with some version of inflation, then no observation can ever test it, and a claim that cannot in principle be proven wrong sits uneasily at the edge of what we can even call science. So look at where we have arrived. To explain why the universe is smooth and flat, we invoked inflation. But inflation requires an undetected field we cannot identify. It may generate an infinity of unobservable universes, and one of its own creators argues it may not be falsifiable at all. We did not so much solve the mystery as relocate it, and possibly deepen it. The patch has a hole of its own. I want to be fair to inflation, though, because it would be easy to leave you thinking it is nothing but hand-waving, and that is not true either. Inflation made at least one prediction that turned out to be spectacularly right, and it is worth knowing about. The theory said that the same violent stretching that smoothed and flattened the universe should also have taken the tiniest quantum flickers, the unavoidable microscopic jitter that quantum mechanics says fills all of space, and blown them up to cosmic size along with everything else. Those stretched out flickers would have become faint ripples in the density of the early universe, slightly denser here, slightly thinner there, and those ripples would have left a specific, calculable pattern in the microwave background, and would have seeded the places where galaxies later formed. When we mapped the microwave sky in detail, the pattern was there, and it matched inflation's prediction remarkably well. So inflation is not just a convenient story, it has a real observational success on its record, and that is why so many cosmologists take it seriously despite its problems. But here is the maddening thing, the thing that keeps the whole subject honest. That same success can be produced by more than one version of inflation, and by some of its competitors too. The prediction that worked does not uniquely single out one theory, and so we are left in an uncomfortable middle place. Inflation is probably telling us something true about the early universe. Some real burst of expansion did likely occur, and yet we cannot say what drove it, cannot rule out that it spawns infinite universes, and cannot fully test the grandest versions of it. It is our best answer, and an open wound at the same time. And that, more than any single fact, is the flavor of modern cosmology. Our best answers and our open wounds are more and more often the very same thing. And notice the pattern beginning to form here, because it is the real subject of tonight. Every time we push on the Big Bang, every time we try to nail down a detail, the theory answers, but the answer comes with a new question attached, often a stranger one than we started with. We are not running out of cracks. We are finding that behind each crack is another, and we have not yet reached the largest crack of all, the one that says almost everything in the universe is made of a substance nobody has ever seen. Part 6. The 95% nobody can name. Here is a sentence that should stop you cold, and I want to say it plainly before I soften it with any explanation. Everything you have ever seen, everything you have ever touched, every star in every photograph, every planet, every atom in your own body, all of it together adds up to about 5% of what the universe is made of. The other 95% is two things, and nobody on Earth knows what either of them is. Let me show you how we ended up making a claim that outrageous, because we did not arrive at it lightly. We were forced there, kicking, by the evidence. It started with galaxies spinning too fast. In the 1970s, an astronomer named Vera Rubin, working with her colleague Kent Ford, was carefully measuring how fast stars orbit around the centers of their galaxies, and she found something that made no sense. The stars far out at the edges of a galaxy were moving just as fast as the stars nearer the center. That should be impossible. Think of the planets in our solar system. Mercury, close to the Sun, whips around quickly. Neptune, far out, crawls along slowly. The gravity holding them weakens with distance, so the outer ones move more gently. Galaxies should work the same way. The outer stars should lag, but they did not. They raced around at full speed, as if held by far more gravity than the visible matter could possibly provide. It was as if every galaxy were embedded in a vast, invisible halo of extra mass. Mass we could not see, mass that gave off no light at all, but whose gravity was unmistakably there. An earlier astronomer, Fritz Zwicky, had glimpsed the same ghost back in the 1930s, studying whole clusters of galaxies and finding they were moving far too fast to stay bound together by their visible mass alone. He had even given it a name, dark matter, and been largely ignored. Rubin's careful, patient work made it impossible to ignore any longer. And then the evidence multiplied. We found that dark matter bends light, exactly as invisible mass should, warping the images of distant galaxies as their light passes through it, a phenomenon we can map directly across the sky. We found a place called the Bullet Cluster, where two galaxy clusters had collided, and the invisible mass had sailed straight through, while the visible gas piled up behind, letting us see the dark matter and the ordinary matter physically separated from each other. And we found its fingerprints printed into the oldest light in the universe, the pattern of the cosmic microwave background, which only fits what we observe if there is roughly 5 times more dark matter than ordinary matter. 6 completely independent lines of evidence, from galaxies to clusters to the infant universe, all pointing at the same conclusion. Dark matter is real. Its gravity is beyond serious doubt, and we have absolutely no idea what it is. For decades, physicists have built exquisite detectors, buried them deep underground to shield them from noise, and waited for a single particle of dark matter to reveal itself. Nothing, not one confirmed detection. We know it is there. We know how much of it there is. We know it makes up about 27% of the universe, and it remains completely, stubbornly anonymous. Think about how odd that situation is for a science. Imagine a detective who can prove, beyond any doubt, that a person was in a room. There are footprints in the carpet, a dent in the cushion where they sat, a warmth still lingering in the chair, a dozen independent traces of their presence. But the detective can never see them, never photograph them, never catch them, no matter how many cameras are set up, no matter how long the stakeout runs. For 50 years the stakeout has continued, deep underground, with the most sensitive equipment ever built, and the suspect has never once shown their face. That is precisely where we stand with dark matter. Its presence is beyond dispute, and its identity is a total blank. Some physicists have even begun to wonder whether we are looking for the wrong kind of suspect entirely, whether dark matter is some exotic particle we have not imagined, or whether the whole framework of our search is somehow mistaken. That doubt, that willingness to question the search itself, is a quiet symptom of a field under strain. And I want to underline just how load-bearing this invisible stuff is, because it is not a minor character. Dark matter is the scaffolding of the entire cosmos. Without it, galaxies would never have formed in the time available. Its gravity is what pulled ordinary gas together into the first structures, what holds galaxies from flying apart, what shapes the vast cosmic web of filaments and voids along which all the visible matter is strung. Everything luminous in the universe, every star and galaxy you have ever admired, formed inside a scaffold of something we cannot see and cannot name. The bright universe is decoration hung on a dark frame, and that is only the 27%. The larger mystery, dark energy, is even further beyond our grasp, and it is the thing we turn to next. But dark matter is only the second largest mystery. The largest came in 1998, when astronomers measuring distant exploding stars discovered that the expansion of the universe is not slowing down, as everyone expected gravity would eventually make it do. It is speeding up. Something is pushing the universe apart, harder and harder, and whatever it is fills all of empty space and makes up about 68% of everything. We call it dark energy. In the Standard Model, it appears as that cosmological constant, the lambda in the theory's name, a fixed energy woven into the vacuum itself. It is the single largest ingredient in the entire universe, and it is the one we understand the least. The way we found it is worth telling, because it is one of the great surprises in the history of science. In the 1990s, two competing teams of astronomers set out to measure how fast the expansion of the universe was slowing down. Everyone assumed it must be slowing. Gravity pulls things together, and the combined gravity of all the matter in the universe should be gently applying the brakes to the expansion, the way a ball thrown upward is slowed by the Earth's pull. The only real question, everyone thought, was whether the universe would eventually stop expanding and collapse back inward, or coast outward forever, at an ever-slowing pace. Nobody expected a third answer. To measure the slowdown, the teams tracked a special kind of exploding star, a Type 1a supernova, which always detonates with nearly the same true brightness, making it a reliable cosmic mile marker. By comparing how bright these explosions appeared to how bright they truly were, the astronomers could measure their distances, and by measuring their light, their speeds. And in 1998, both teams arrived, independently and to their own disbelief, at the same impossible result. The distant supernovae were fainter than they should have been. The expansion was not slowing down, it was speeding up. Something was pushing the universe apart, overwhelming the collective gravity of all the matter in it, and accelerating the growth of space itself. The discovery was so unexpected that the astronomers spent months hunting for errors before they believed it, and it eventually earned a Nobel Prize. But it left us with a universe whose dominant feature is a repulsive push we cannot explain, growing stronger in its effect as the cosmos expands and the matter thins out. Dark energy is not a quiet background detail. It is the thing that will ultimately determine the entire fate of the universe, driving the galaxies apart faster and faster until, in the far future, the sky itself goes dark, and it is the single most mysterious ingredient in the whole of physics. So let me put the whole recipe in front of you, and let me give you a moment to sit inside it. Picture the entire universe drawn as a single circle, sliced up by what it contains. Almost all of that circle is dark. 68% of it, more than 2/3, is dark energy, a shade we cannot explain. Another 27% is dark matter, a second shade we cannot see. And then, somewhere on that circle, you have to look closely to find it, is a thin, bright sliver, 5%. And that sliver is everything. Every star you have ever seen, every planet, every galaxy in every deep field image that ever took your breath away, every cloud of gas between the stars, every atom in your hands, in the chair beneath you, in the air you are breathing, in the body of every person you have ever loved. All of it, the entire visible cosmos, everything that anyone has ever looked at through any telescope in all of history, is that one small, bright sliver, floating in an ocean of two things nobody can name. I want you to really feel that, because it is easy to hear it as a fun fact and move on, and it is not a fun fact. It is one of the strangest situations science has ever found itself in. The overwhelming majority of reality is invisible to us and unexplained by us, and everything you have ever cared about, everything that has ever mattered to you, is made entirely of the 5% that the universe seems to treat as an afterthought, a rounding error, a thin, bright rind on the outside of a vast, dark thing. And here is the sharpest edge of it. This is the same theory, remember, that predicts the infant universe's temperature to better than 1 part in 1,000. That triumph is real, but it is a triumph that comes with a confession attached. To make the equations work, to match the sky so beautifully, the theory has to assume that almost everything in the universe is a placeholder. Two names, dark matter and dark energy, that are really just labels for two enormous holes in our knowledge. Dark energy, that lambda in the model's very name, is in the end a placeholder wearing a Greek letter, a confession dressed up as physics. Hold on to that phrase, a placeholder wearing a Greek letter, because we are going to come back to it, and when we do, that placeholder is going to start moving. Part 7. The number the universe will not agree on. Of all the cracks in the Big Bang, this is the one that keeps cosmologists up at night. It is the sharpest, the most precise, the hardest to explain away, and it has done something that a crack in a good theory is never supposed to do. It has gotten worse the harder we have looked. The crack is about a single number. It is called the Hubble constant, and it measures the most basic thing you can ask about the universe. How fast is it expanding? Right now. It is, in a real sense, the current growth rate of everything, and there are two very different ways to measure it. Two roads to the same number, and the two roads no longer arrive at the same place. The first road starts in the early universe. We take that oldest light, the cosmic microwave background, mapped in exquisite detail by the Planck satellite. Buried in the precise pattern of its warm and cool spots is all the information needed to calculate how fast the universe should be expanding today. You feed the early universe map into the standard model, turn the mathematical crank, and out comes a prediction for the expansion rate. That number is about 67.4. The units are kilometers per second per megaparsec, but you do not need to worry about the units. Just hold on to the number. From the early universe, 67.4. Now here is something important. That first road relies on the Planck satellite and on the standard model, so you might worry the number is only as good as those assumptions. But there is a completely independent early universe method, a vast survey called DESI, that maps the three-dimensional positions of millions of galaxies and reads the expansion rate from a kind of frozen sound wave imprinted across them. DESI does not rely on Planck at all, and DESI gives about 68.5, slightly different method, essentially the same answer. The early universe, measured two independent ways, says the expansion rate is somewhere around 67 to 68.5. The second road starts here, nearby, in the late universe, the universe of today. Instead of calculating the expansion rate from the infant cosmos, we measure it directly. We find stars whose true brightness we know, a special kind of pulsing star called a Cepheid, and we use them to measure precise distances to nearby galaxies. Then we watch how fast those galaxies are receding, and we build what is called a distance ladder, each rung calibrated against the one below it, reaching out into the expanding universe. A team called SH0ES has spent years perfecting exactly this measurement, and the number they get is about 73. 67 to 68.5 from the early universe, 73 from the nearby one, and those two numbers do not agree. Now, you might think, 73 versus 68, that is not such a big gap, only a few points. But in a measurement this precise, it is an enormous gap. It is a disagreement of about 8 or 9%, and both sides have error bars, ranges of uncertainty, and those error bars do not overlap, not even close. When physicists measure how significant a disagreement is, they talk in units called sigma, and 5 sigma is the gold standard, the threshold at which they are willing to announce a discovery, a real effect that is not a fluke. The gap between the early universe number and the late universe number has now reached about 5 sigma. This is not noise. By the field's own strictest standard, it is real. And here is the part that turns unease into something colder. For years, everyone assumed this disagreement would go away. Surely, they thought, one side has made a mistake, some subtle error in the distance ladder, some overlooked wrinkle in the early universe calculation, and as our measurements improve, the two numbers will slide together and meet in the middle, the way discrepancies in science usually do. That is the normal course of things. Better data resolves disagreements. But that is not what happened. As the measurements got better, as the SH0ES team refined their distance ladder, and the early universe surveys sharpened their maps, the two numbers did not converge. The error bars shrank, and the gap held. If anything, the disagreement grew more significant, not less, because the more precise each side became, the more confident each was in its own answer, and the more impossible it became to blame the gap on sloppiness. People tried to pin it on a single faulty measurement, one bad rung in the ladder, and those attempts have largely failed, because the disagreement survives even when you swap out individual pieces of the analysis. Stop and feel the strangeness of that. We built the finest instruments our species has ever made. We pointed them at the simplest question you can ask the universe: how fast are you growing? And the better our tools got, the further apart the two answers drifted. This is the opposite of how progress is supposed to work. Progress is supposed to converge on the truth. Here, progress pulled the two truths apart. The universe, asked its own growth rate, gives one answer when you ask it about its infancy, and a different answer when you ask it about today, and it will not reconcile them, no matter how carefully we listen. And notice something important about the structure of this disagreement, because it is subtle, and it is the reason the tension is so hard to dismiss. The early universe number is not really a direct measurement of today's expansion rate at all. It is a prediction. You measure the infant universe, you assume the standard model is correct, and you calculate forward, across nearly 14 billion years, to what the expansion rate must be now. The late universe number, by contrast, is a direct measurement of the here and now, no long extrapolation required. So the two numbers are answering the question in fundamentally different ways. One says, given everything we think we know, the expansion today should be this. The other says, when we actually go and measure the expansion today, it is that. And the two disagree. That framing matters because it tells you where the problem most likely hides. If the early universe prediction and the late universe measurement disagree, then either one of the two measurements is subtly wrong, and teams have hunted for that error for years without finding it. Or, far more interestingly, the assumption in the middle is wrong. The bridge you walk across to get from the infant universe to today, the standard model itself, may have a missing plank somewhere in the middle of cosmic history. Something may have happened between then and now that the model does not include, some ingredient, some event, that would change the arithmetic and reconcile the two numbers. In other words, the Hubble tension may not be a measurement problem at all. It may be the universe telling us that our story of what happened between the beginning and now is incomplete. And if that is what it is, then this single stubborn number is a signpost, pointing directly at new physics, hidden somewhere in the vast stretch of time we thought we already understood. This is the moment where you can feel the phrase, "we have been circling all night." The more we look, the less it agrees with itself. Say that quietly to yourself. The more we look, the less it agrees with itself. That is not just a fact about the Hubble constant. As we are about to see, it is starting to look like the signature of the whole enterprise. And there is a fresh check coming. A new space telescope called Euclid is mapping the structure of the universe from yet another angle, and when its main results arrive, they will offer a third, independent opinion on which side, if either, is right. For now, the two numbers hang there, refusing to meet. Part 8. Step back and look at the shape of it. Let us pause here, at the midpoint, and do something the individual cracks do not let you do. Let us step back far enough to see the whole wall at once. We have been walking, crack by crack, deeper into the trouble, and it would be easy, in the middle of it, to lose the thread and think of these as a scattered collection of unrelated problems. A hole at the beginning, a too smooth sky, a patch that raises its own questions, a missing 95%, a number that will not agree with itself. It would be easy to file each one separately and move on, but I do not think they are separate. I think, when you stand back, they form a pattern, and the pattern is the real story. So let me first say clearly what these problems are not, because this matters enormously, and it is where most people go wrong. Not one of the cracks we have looked at tonight comes from the fringe. Not one of them is the pet theory of a crank, or a misunderstanding by someone who does not know the physics, or a controversy manufactured by people with an agenda. Every single one is a genuine, hard problem sitting inside the best data from the best instruments, acknowledged by the most mainstream, most respected cosmologists alive. The singularity is a theorem proven by Penrose and Hawking. The horizon problem is why inflation was invented in the first place, by physicists at the center of the field. The dark sector rests on 6 independent lines of rock-solid evidence. The Hubble tension is measured by rival teams of world-class scientists who would love nothing more than to prove each other wrong, and cannot. These are not attacks on cosmology from the outside. They are cosmology's own honest accounting of what it cannot yet explain. And now, with that established, look at the shape they make together. Because there is something they all have in common, and once you see it, you cannot unsee it. The Big Bang model is spectacularly successful at the coarse level, at the big, broad, sweeping features. It nails the overall expansion. It nails the black-body glow of the relic radiation. It nails the broad recipe of the light elements. When you ask the model a rough question, it gives a stunningly right answer, but every one of the cracks we have found appears exactly where we push for precision, the exact rate of expansion, the exact nature of the 95%, the exact behavior of the beginning, the exact reason for the smoothness. It is when we zoom in, when we demand the fine detail, that the model starts to come apart in our hands. And that is genuinely backwards from how theories are supposed to behave. Normally, when a theory is fundamentally right, refining your measurements makes the discrepancies shrink. You look closer, and the small disagreements resolve into agreement, and your confidence grows. That is what maturity looks like in a science. But here, the opposite is happening. Here, looking closer, is manufacturing the disagreements. The precision is not healing the theory. The precision is what is breaking it. The sharper our vision becomes, the more the cracks multiply and widen. There is a useful way to think about why this happens, and it comes from the history of science. Every theory has a resolution, a level of detail below which it simply stops being accurate, even if it works beautifully above that level. Newton's laws of motion are perfect for building a bridge or launching a cannonball, and they remain perfect right up until you start measuring things moving near the speed of light, or objects as small as atoms. At everyday resolution, Newton is flawless. Push to finer resolution, and cracks appear, not because Newton was foolish, but because his theory was an approximation that only revealed its seams when the measurements got sharp enough to see them. The cracks were always there. We just could not see them until our instruments improved. That, I suspect, is what we are watching happen to the standard model of cosmology, in real time. For decades our measurements were coarse enough that the model looked complete, seamless, final. Now, for the first time, we are measuring the universe finely enough to see below the model's resolution, into the region where its approximations start to fray. The Hubble tension, the dark energy hints, the early galaxies, the anomalies in the ancient light, these may all be the same thing, wearing different masks. They may all be the seams of an approximation, finally becoming visible because we finally built eyes sharp enough to see them. If that is true, then the crisis is not a catastrophe. It is a threshold. It is the moment a good theory reveals, through its own tiny failures, that a better one is waiting just underneath. And the second half of this video is where those tiny failures start arriving fastest. From the newest instruments ever built, beginning with a discovery that the largest ingredient in the universe may not be the fixed, unchanging thing we always believed. There is a name for what this feels like from the inside, and it is worth saying plainly, without drama. This is what a paradigm under strain looks like. Not a theory that is wrong, exactly. Not a lie to be thrown out, but a framework that has been pushed right up to the edge of what it can do, and is beginning to show, in its finest details, that it is an approximation of something deeper that we have not yet found. The cracks are not random. They are all whispering the same thing. They are all telling us that our beautifully successful model is not the final word. That it is, in some sense we do not yet fully understand, incomplete, and that the missing pieces are not small. Hold that idea gently, because it is where we are heading. But do not settle on it yet, because we are only halfway down. So far we have looked at the cracks that have been known, in one form or another, for years or decades. Now the story turns, and it turns toward the most recent discoveries, the ones arriving right now, in the last months and years, from the newest instruments ever pointed at the sky. And the newest discoveries are not closing the cracks, they are opening new ones, starting with the possibility that the placeholder we could not explain, the largest ingredient in the universe, is not even the constant we assumed it was. Part 9. The constant that may not be constant. I asked you to hold on to a phrase a little while ago, a placeholder wearing a Greek letter. That was dark energy, the lambda in the model's name, the mysterious energy of empty space that makes up 68% of the universe and drives its accelerating expansion. For a quarter of a century, we have had almost no idea what dark energy is. But we thought we knew one thing about it, one comforting, stabilizing thing. We thought it was constant. That word matters more than it sounds. A cosmological constant means an energy density that is the same everywhere in space and, crucially, the same at every moment in time. It does not grow. It does not fade. It was the same in the early universe as it is today and as it will be forever. This constancy is not a small detail. It is the single assumption that the entire standard model is built around. It is why the model is called lambda CDM. The lambda is the constant. If dark energy is truly constant, the model holds its shape. We do not know what dark energy is, but at least we know it sits still. And then, in 2024 and 2025, that assumption began to wobble. The wobble came from DESI, the same enormous galaxy survey I mentioned earlier, the largest three-dimensional map of the cosmos ever made. DESI has charted the positions of tens of millions of galaxies and quasars across billions of years of cosmic history, and because it can see so far, it can effectively watch how dark energy has behaved over time, comparing its strength in the distant past to its strength more recently. In its second major data release, DESI reported something that sent a quiet shock through cosmology. When its map was combined with the cosmic microwave background and with distant supernova measurements, the data fit better, noticeably better, if dark energy is not constant at all, but changing. Let me be careful and precise about what the data suggest, because this is a live and contested result, and it deserves honesty rather than hype. The pattern in the numbers points to a dark energy that was somewhat stronger in the distant past and has been weakening as the universe ages. Physicists describe the strength of dark energy with a value they call its equation of state, and the DESI results favor a scenario where that value has drifted across a particular threshold, a threshold that simple, well-behaved models of dark energy are not supposed to be able to cross. That crossing happened, if it happened, a few billion years ago, and crossing it demands a kind of dark energy, far more exotic and strange than a simple constant, something dynamic, something alive, something that evolves. Now, how sure are we This is where the intellectual honesty of the channel matters. The statistical strength of this hint sits somewhere between about 2.8 and 4.2 sigma, depending on exactly which set of supernova data you fold in. Remember our gold standard from the Hubble tension, 5 sigma, the discovery threshold. This has not reached it. It is suggestive. It is tantalizing. It is being argued about fiercely in the literature right now, with some cosmologists convinced it is the first real sign of new physics, and others cautioning that it may yet dissolve as the analysis is refined. It is not settled. I want you to hold it exactly as loosely as the evidence demands, no tighter. But let me tell you why even a hint at this level has cosmologists sitting up straight. Because it connects to something we already touched. If dark energy is weakening over time, that changes the whole future of the universe, and it also might quietly loosen some of the other knots we have found. A dark energy that behaves differently than a fixed constant would alter the arithmetic that bridges the early universe to today, which is exactly the bridge where the Hubble tension lives. It is at least possible, and this is what makes the whole thing electric, that several of our cracks are not separate problems at all, but different symptoms of a single missing piece. That the reason the expansion rate will not reconcile, and the reason the ancient light has faint anomalies, and the reason dark energy seems to be shifting, all trace back to one thing about the universe that our 6-number model leaves out. Nobody knows if that is true, but the possibility that the cracks are connected, that they are all fingers pointing at one hidden door, is precisely why this is the most exciting time to be doing cosmology in a generation. And there is a deeper discomfort lurking underneath the DESI result, one that goes beyond any single number. A true cosmological constant, whatever else you say about it, is at least conceptually clean. It is a fixed property of empty space, the same forever, needing no explanation for why it changes, because it does not change. But a dark energy that evolves, that was stronger and is now weakening, demands an answer to a much harder question. What is it, physically, that is doing the evolving? What field, what substance, what new law of nature is responsible for the largest component of the cosmos, gradually shifting its strength over billions of years? A constant is a mystery you can shelve. A moving dark energy is a mystery that stares back at you and demands to be explained. So if the placeholder really is moving, we have not just lost a comfortable assumption, we have inherited a far more urgent question, one that the standard model, as it stands, has absolutely no answer for. But feel what it would mean if it holds. For 25 years, we could not explain dark energy, but we could at least treat it as a fixed, unchanging feature of reality, a constant we could name, even if we could not understand. Now the newest, largest map of the universe is suggesting that even that constancy may be an illusion, that the placeholder we could not explain is not even sitting still. The placeholder wearing a Greek letter turns out, perhaps, to be moving, and if it is moving, then the standard model does not need a small patch or a minor correction. It needs a whole new ingredient, a new kind of physics governing the largest component of the universe, because the lambda that the entire framework is named after, the constant at the very heart of it, would no longer be a constant at all. Notice, once again, the direction of the surprise. This did not come from someone doubting cosmology from the outside. It came from the single most ambitious mapping project the field has ever undertaken, doing exactly what it was built to do, looking more closely than anyone ever had. And looking more closely did not steady the picture. It set the largest piece of it trembling. The better the map, the less certain the thing we were most certain of. And the newest instruments are only getting started. Part 10. The galaxies that should not be there yet. In the summer of 2022, humanity switched on the most powerful eye it has ever built and pointed it at the deep past. The James Webb Space Telescope sits about 1 million miles from Earth, chilled to within a whisper of absolute zero, its great golden mirror unfolded in the dark, and it can see fainter, older, more distant things than any instrument before it. It was built, among other reasons, to look back toward the very first galaxies, the ones that lit up when the universe was young, and almost immediately it began sending back images that did not fit. Let me put you in the moment, because it is a genuinely strange one. The telescope stares at a single dark patch of sky, a patch that looks empty to lesser instruments, and it holds that stare for hours, gathering the faintest trickle of light. Photons that left their source more than 13 billion years ago, that have been traveling across the expanding universe since it was an infant, finally fall onto the mirror and are counted, one by one. And then the image resolves on the screens back on Earth. And there, in a place where the standard model says there should be, at most, small, faint, half-assembled scraps of galaxies just beginning to come together, sits something else. A galaxy, bright, large, gathered, far more grown up, far more massive than it has any right to be at that age. The universe, at the moment we are seeing these galaxies, is only about 300 to 500 million years old. That sounds like a long time, but on cosmic scales, it is the blink after the beginning, a tiny fraction of the 13.8 billion years the universe has lived so far. In that model, structure builds up slowly. Gravity needs time to gather gas into stars, and stars into galaxies, and small galaxies into large ones. It is a patient process, and the standard timeline says that this early, the universe should still be sketching its first rough drafts of galaxies. Instead, Webb was showing us galaxies that looked too big, too bright, and too many, appearing too soon. Astronomers, only half joking, started calling them impossible early galaxies, and some called the brightest and earliest of them the universe breakers. This is the kind of moment that makes the whole subject feel alive, because you can almost feel the timeline we so carefully wrote down, failing to match the sky in real time. We built a schedule for how the cosmos should have grown, and then we built an eye sharp enough to actually watch it grow, and the eye showed us the universe running ahead of schedule, doing things earlier than the schedule allowed. Now, here is where I have to keep the channel's promise of honesty, because this story has genuinely softened, and pretending otherwise would be a disservice to you. In the time since those first alarming images, careful follow-up work has taken some of the edge off. A study led by a young astronomer named Catherine Chworawski and others like it showed that several of these galaxies are not as massive as they first appeared. Some of their brightness, it turns out, comes not from an impossible amount of stars, but from other sources, from black holes at their centers, feeding rapidly and glowing fiercely, or from unusually intense bursts of star formation that make a modest galaxy look far heavier than it is. When you account for those effects, some of the impossible galaxies become merely surprising, and the crisis for the model eases. But, and this is the important but, it has not gone away. Not all of the objects can be explained away so cleanly. Some remain genuinely difficult to fit into the standard timeline, and Webb has kept delivering surprises, including the discovery, early in 2025, of a large, beautifully formed spiral galaxy, nicknamed the Big Wheel, existing far earlier than such a mature, orderly structure should have been able to assemble. There is also a whole population of strange objects Webb keeps finding, compact and intensely red, that astronomers have taken to calling little red dots, and which nobody has fully explained yet. The picture is not one clean, decisive break with the model. It is messier and more honest than that. It is the early universe, seen clearly for the first time, turning out to be a little ahead of itself, a little off script, in ways we are still arguing about. I find it worth slowing down here to appreciate what these galaxies actually are, because it deepens the strangeness. When you look at one of these early objects, you are not looking at a picture of how it looks now. You are looking at light that left it more than 13 billion years ago and has been in transit ever since. The galaxy you see froze into that image when the universe was an infant, and everything that has happened to it in the 13 billion years since is invisible to you, still traveling, still on its way, light we will never live to receive. So Webb is not photographing the early universe. It is receiving a message from it, a message that has been crossing the widening dark for almost the entire age of existence, only to arrive, at last, on a gold mirror 1,000,000 miles above a small blue planet, and to say, quietly, we were already here, already grown, already bright, sooner than you thought we could be. And there is a reason this particular kind of surprise cuts so deep into the model, more than you might expect. Structure formation, the slow gathering of gas into stars and stars into galaxies, is supposed to be the part of cosmology we understand best. It is driven by gravity, the most familiar of the forces, acting on the dark matter scaffolding over long stretches of time. It is not exotic quantum weirdness or unexplained dark energy. It is just gravity, patiently pulling things together, and we have detailed computer simulations of exactly how fast it should proceed. So when the real universe assembles big, bright, orderly galaxies faster than those simulations allow, it is not a small technical footnote. It is a challenge to our understanding of the one process we thought was straightforward. Even gravity, even the patient, familiar gathering of matter, may be following a script we have not fully read. And if the simple part is off script, it makes you wonder, quietly, uneasily, how much of the rest we truly have right. And that, in a way, is the whole theme of tonight in miniature. We built our sharpest instrument ever, and pointed it at the deep past, expecting confirmation, and got, instead, a set of new questions. The closer we looked at the beginning, the less tidily it matched the story. Not a refutation, a complication, another crack, thin and real, running through the timeline. And there is one more place to look before we can make sense of all of them together, and it is the most sacred piece of evidence the Big Bang has, the oldest light in existence, which turns out to have a few smudges on it that should not be there. Part 11. The smudges on. The baby picture. If the Big Bang model has a crown jewel, a single piece of evidence that more than any other convinced the world it was right, it is the cosmic microwave background. We have circled it several times tonight, but now I want to look straight at it, because even this, even the theory's greatest triumph, has something quietly wrong with it. Remember what this light is. About 380,000 years after the beginning, the universe had cooled just enough for the first atoms to form, and in that moment it became transparent, and the light that was flying around at that instant was set free to travel forever. It has been traveling ever since, stretching as the universe expanded, until today it reaches us as a faint microwave glow coming from every direction in the sky. It is, quite literally, the oldest light there is, a photograph of the universe as an infant, taken when it was less than 1,000th of its current age, and it is almost perfectly uniform. Its temperature is the same everywhere to about 1 part in 100,000, and its glow matches the ideal thermal spectrum, called a blackbody, more perfectly than any object we have ever measured in a laboratory. When we first mapped it in detail, it was a stunning confirmation of everything the theory predicted. Almost perfect, almost uniform, but not quite. And the not quite is where the strangeness lives. Lie back for a moment and imagine you could see this microwave glow directly, wrapped around the whole sky, a faint, even warmth in every direction. Now imagine looking harder at the largest patterns in it, the biggest, broadest features. And here is what you would find, hidden in the oldest light in the universe. First, there is a cold spot. In the direction of the constellation Eridanus, there is a patch of the sky that is unusually large and unusually cold. Colder and bigger than the random statistics of the model comfortably allow. It is not impossible by chance, but it is odd enough that it has its own name and its own long-running debate. Second, and stranger, there is something cosmologists have given the only half-joking name, the axis of evil. The two largest scale patterns in the microwave sky, the broadest ripples of warm and cool, appear to be aligned with each other. That alone is unexpected. But here is the unsettling part. They also appear to be aligned, roughly, with the plane of our own solar system and with the direction of our own motion through space. Think about how strange that is. The cosmic microwave background is supposed to be the universe at its most impartial, a relic from before there were stars or planets or people, with no reason on Earth to care about the particular little plane our particular little planet happens to orbit in. The universe, on the largest scales, is supposed to have no preferred direction at all, and yet the oldest light seems, faintly, impossibly, to pick out a direction, and that direction seems to have something to do with us. Third, the very largest scale ripples are weaker than the model predicts, as though some of the biggest features were quietly missing. And fourth, the two halves of the sky do not quite match, one hemisphere showing slightly more fluctuation than the other, again breaking the assumption that the universe should look statistically the same in every direction. Now, I need to be honest about the strength of these, because honesty is the whole point. Each of these anomalies, taken on its own, is of modest statistical significance. Any one of them could be a fluke, a roll of the cosmic dice, or a subtle contamination from our own galaxy's foreground glow that we have not perfectly removed. If there were only one, few people would lose sleep over it. But there are several. They were seen by two completely independent satellites, the earlier WMAP and the later, more precise Planck, and they have stubbornly refused to go away as the measurements improved. And that persistence, that refusal to vanish, is exactly the pattern we keep meeting tonight. Sit for a moment with the full weirdness of it. The closest thing we have to a baby picture of everything, the relic light of creation itself, has a handful of faint smudges on it, and the smudges are not random. They line up, gently and inexplicably, with the plane your own world moves through. Either it is a coincidence, a trick of statistics, and foregrounds that will eventually be explained, or the universe is not quite as featureless, as smooth, as impartial as the theory needs it to be. And I do not want you to feel that as fear. I want you to feel it as wonder. The particular vertigo of realizing that the oldest, calmest, most fundamental thing we can observe still has a secret in it we have not cracked. Even the crown jewel has a flaw, and the flaw is pointing, ever so faintly, back toward home. Let me be scrupulously fair here, because this is exactly the kind of anomaly where it is easy to slide from science into something less careful. The most likely mundane explanation for the apparent alignment with our solar system is not that the universe cares about us. It is that some faint glow from our own galaxy, or from dust in our own solar system, has not been perfectly subtracted from the maps, leaving a residue that happens to line up with local structures simply because it comes from local structures. That is a real possibility, and many cosmologists suspect it is the answer. If so, the axis of evil is not a message from the cosmos, but a smudge on our own lens that we have not fully wiped away. This would be the deflating, ordinary resolution, and it may well be the correct one. But here is why the anomalies still matter, even if each one eventually turns out to be mundane. It is the pattern, again, that unsettles. We keep finding these things, small anomaly after small anomaly, each individually explainable, each individually dismissible, but together, forming a persistent drizzle of features that the clean, perfect model did not predict. And the model is supposed to be the perfect one. The microwave background is where the standard model is at its most triumphant, its most precise, its most trusted. If even here, in the theory's holy of holies, there are stubborn little features we keep having to explain away, then perhaps the perfection was always slightly overstated. Perhaps the smoothness we celebrated was smooth enough to convince us, but not quite smooth enough to be the whole truth. And that quiet doubt, arriving even at the model's proudest moment, is the last of the new cracks. Now we go down, one final time, to the oldest cracks of all, the ones that have been in the foundation from the very start. Part 12. The cracks that were always in the foundation. We have spent the last few parts on the newest cracks, the ones arriving from the newest instruments. But before we can pull the whole picture together, I have to take you down to the oldest cracks of all, the ones that were in the foundation from the very beginning, that have been sitting there for decades, patched over or quietly set aside, waiting, because they are part of the pattern too, and some of them are the deepest of all. Start with the one physicists sometimes call the worst prediction in the history of science, and they are not exaggerating. Remember dark energy, that energy of empty space that fills the universe and drives its acceleration. Well, quantum physics has something to say about empty space. According to quantum field theory, our best and most tested framework for the behavior of the very small, empty space is not truly empty at all. It seethes with activity, with fields fluctuating, with particles flickering in and out of existence, and all that activity should carry energy. So physicists did the natural thing. They used quantum theory to calculate how much energy empty space should contain, and then they compared that prediction to the amount of dark energy we actually measure in the universe. The two numbers disagree, and they do not disagree by a little. They disagree by a factor of, at the extreme estimates, 10 to the power of 120. That is a 1 followed by 120 zeros. It is difficult to even describe how catastrophic a mismatch that is. It is not that the theory is a bit off. It is that our best theory of the small and our best measurement of the large disagree about the energy of empty space more completely than any two numbers in the history of physics have ever disagreed about anything. We have simply, quietly, learned to live with it, because we have no idea how to fix it. That is the cosmological constant problem, and it has been sitting under the foundations of cosmology, unresolved, for a very long time. To feel the size of that mismatch, forget the exponents for a moment, and try an image. Imagine you predicted the weight of a single grain of sand, and your prediction came out heavier than the entire observable universe, every star and galaxy in it combined, and not by a little, but by a margin so vast that the universe's true weight was a rounding error next to your answer. That is roughly the flavor of being off by 120 orders of magnitude. It is not a near miss. It is the most spectacular failure of quantitative prediction in the history of the subject, made by the very theory, quantum field theory, that in every other arena is the most accurately tested framework humans have ever devised. The same physics that predicts certain particle properties correctly to 12 decimal places, an almost unbelievable precision, gets the energy of empty space wrong by a factor with 120 zeros in it. And the strangest part is that the universe seems to have arranged for nearly all of that enormous predicted energy to cancel out, leaving just the tiny, delicate whisper of dark energy we actually observe. A whisper just strong enough to accelerate the cosmos, but not so strong as to have ripped it apart before galaxies could form. Why the cancellation is so nearly perfect, and yet not quite perfect, is a mystery no one has cracked. It sits under everything, quietly, like a crack in the bedrock that we have all agreed not to look at too closely. Now consider a second deep crack, and this one is about why there is anything here at all. In the hot early universe, energy was constantly turning into matter, and here is the rule. When energy turns into matter, it makes matter and antimatter in exactly equal amounts. A particle and its mirror image antiparticle, always in pairs. And when a particle of matter meets its antiparticle, they annihilate, vanishing back into pure energy. So the early universe should have made precisely equal amounts of matter and antimatter, and then all of it, every last bit, should have annihilated, leaving a universe of nothing but radiation. No atoms, no stars, no planets, no you. A cosmos of pure light and empty space. But that is not what happened, obviously, because you are here. Somehow, for reasons we still do not fully understand. The early universe made a tiny imbalance. For every billion particles of antimatter, it made about 1,000,000,001 particles of matter. That one extra particle per billion, that impossibly slight surplus, survived the great annihilation when everything else cancelled out. And that leftover 1 in a billion is everything. It is every atom in every galaxy. It is the entire material universe. All of it is the rounding error that the early cosmos happened, for unknown reasons, to leave behind. Why the imbalance exists at all, why matter won by that razor-thin margin instead of tying with antimatter and leaving nothing, is an open question. The very existence of stuff is unexplained. And here is a third, perhaps the most mind-bending of all. For the universe to work the way it does, for time to flow forward, for the second law of thermodynamics to hold, for the whole ordered unfolding of cosmic history to be possible, the universe had to begin in an extraordinarily special, extraordinarily ordered, low disorder state. Just how special? The physicist Roger Penrose, the same one whose name is on the singularity theorems, tried to calculate the odds of the universe beginning in a state as ordered as ours by chance. The number he arrived at is so large it breaks language. The precision required was about 1 part in 10 to the power of 10 to the power of 123. That is not 10 to the 123. It is 10 to the power of a number that is itself 10, followed by 123 zeros. It is a number so vast you could not write out its zeros if you used every particle in the observable universe as ink. The universe began in a state of order so precise, so finely chosen, that we have no physical explanation for it whatsoever. It is simply an initial condition we have to assume, and no one knows why it holds. And there is even a small stubborn crack in one of the model's proudest successes. The theory predicts the amounts of the lightest elements forged in the first few minutes of time, and for hydrogen and helium, the predictions are magnificent, matching what we observe with beautiful precision. But for lithium, the third lightest element, the model predicts about 3 times more than we actually find in the oldest stars. This is the lithium problem, and despite decades of effort, there is no agreed solution. Even in its greatest triumph, the cooking of the first elements, the model has a persistent, nagging shortfall it cannot account for. I want to draw out something about the low entropy beginning in particular, because it may be the most profound of all these old cracks, and it hides a secret about your own life. The reason time flows forward, the reason you remember the past and not the future, the reason a cup can shatter but never spontaneously reassemble, the reason the whole universe has a direction to it at all, traces back to that extraordinarily ordered beginning. Order tends to decay into disorder, never the reverse. That one-way slide from order toward disorder is what gives time its arrow. But that slide can only happen if you start with order. If the universe had begun in a state of disorder, there would be no slide, no arrow, no flow of time as we experience it. So the fact that you can remember this morning, the fact that your life has a before and an after, the fact that anything ever happens at all in a particular sequence, all of it depends on the universe having begun in that absurdly, inexplicably ordered state. The arrow of time itself is a debt we owe to an initial condition that no one can explain. When you feel time passing tonight, you are feeling the consequence of a mystery physics has never solved. And this is the point I most want you to take from this part. These old cracks are not lesser problems than the shiny new ones from the telescopes. In some ways they are greater, because they touch the very possibility of a universe like ours existing at all. Why is there matter instead of nothing? Why did time have a direction? Why is empty space not 120 orders of magnitude more energetic than it is, which would have torn the cosmos apart before a single atom formed? Each of these is a place where the smooth, confident summary of the Big Bang quietly requires either a fine-tuning so precise it defies belief, or an ingredient we cannot name, or an initial condition we simply have to assume and cannot justify. The foundation was never the seamless slab we were shown in school. It was always laced with these deep fractures, load-bearing questions holding up the whole structure, unanswered. We just do not usually look down at them. Tonight we did. And now, having seen all of it, the old cracks and the new, the whole wall at once, we are finally ready to ask what it all means. I lay all of these before you, not to bury you in problems, but so that you can see the truth of the foundation. It was never the seamless, polished thing the summary suggests. It was always shot through with these deep, unanswered questions. The worst prediction in physics, the unexplained existence of matter itself, the absurdly ordered beginning, the missing lithium. They were there all along, and now, standing among both the oldest cracks and the newest, with the whole wall visible at last, we are finally ready to ask the real question. What does all of this actually mean? And the answer, I promise you, is not what the loudest voices on either side will tell you. Part 13. What the less sense actually means. So here we are, at the end of the long walk, standing back and looking at the whole of it. A theory with a hole burned in its very beginning, where its own equations dissolve into infinity. A universe too smooth and too flat to explain, patched by an inflation we cannot detect and may not be able to test. A 95% made of two things nobody can name, one of which may not even be the constant we assumed. A most basic number that splits into two answers and refuses to reconcile. Galaxies that grew too fast, a baby picture with smudges that point at us, and beneath it all, ancient cracks in the foundation, the worst prediction in physics, the unexplained existence of matter, a beginning ordered beyond any hope of chance. And the question that has been waiting for us all night is finally ripe. What does it mean that the more we study the Big Bang, the less sense it makes? Let me first tell you what it does not mean, because two loud groups of people will try to tell you otherwise, and both of them are wrong. It does not mean the Big Bang has been debunked. When Webb sent back those early galaxies, corners of the internet erupted with the claim that the Big Bang was finished, exposed as a lie, overturned at last. That is simply false, and now you know enough to see exactly why. Nothing we have looked at tonight touches the core claim that the universe was once hot and dense and has been expanding. That claim rests on the redshift of distant galaxies, the existence and precise spectrum of the microwave background, and the abundances of the light elements, and it is as solid as anything in science. Every crack we found was in the fine detail, in the precise version of the theory, not in its foundation. The people announcing the death of the Big Bang have mistaken strain on the model's fine structure for the collapse of its core, and those are not remotely the same thing. But it also does not mean, at the other extreme, that everything is fine, that these are just tidy little puzzles that clever people will soon file away, and that the standard model is essentially the final word. Because the pattern we have seen is too consistent, too directional to wave off. The cracks are not shrinking. Several of them are widening, and they are widening precisely as our vision sharpens, which is exactly backwards from how a finished theory behaves. So if it is neither debunked nor finished, what is it? Here is the reframing that I think the evidence actually points to, and it is quieter and stranger and, to my mind, far more thrilling than either extreme. The coarse Big Bang, the hot, dense, expanding universe, is bedrock. That is not what is cracking. What is cracking is something subtler. It is the assumption we quietly made, in our success, that a model built from 6 numbers could describe absolutely everything, down to any level of precision we cared to demand. For a long time, that assumption held, because our measurements were not fine enough to test it. The model was a magnificent approximation, and at the resolution we could see, an approximation was indistinguishable from the truth. But now, for the first time, we have built instruments precise enough to see past the approximation. And what they are showing us, in the Hubble tension, and the evolving dark energy, and the early galaxies, and the smudges in the ancient light is the texture of the places where the approximation ends and something deeper begins. That is what the less sense actually means. It does not mean the universe is refusing to make sense. It means our current story, for all its power, is a first draft. And I told you, long ago in this video, to hold on to that phrase, a first draft, and here is where it comes back and changes its meaning. Back then it described the popular cartoon of the Big Bang, the exploding dot, a crude sketch that the real theory replaced. But now I mean something larger. The whole standard model, the 6 numbers, the constant lambda, the cold dark matter, the inflation, is itself a first draft. An astonishingly good first draft, good enough to predict the infant universe to a fraction of a percent, but a first draft all the same. And a first draft this good is not a failure. It is a promise. It is a promise about how extraordinary the next draft is going to be. Because listen to what the cracks are actually doing. The more we look, the less it agrees with itself. We said that phrase first at the Hubble tension, and it felt like dread. But turn it over now, at the end, and hear it differently. A theory that quietly disagrees with itself, at the exact edge of our sharpest measurements, is not a theory dying. It is a theory pointing. Every one of those disagreements is a finger, aimed at the specific place where new physics is hiding. The Hubble tension is telling us there is something we do not understand about the expansion. The evolving dark energy is telling us there is a new ingredient in the largest part of the cosmos. The early galaxies are telling us structure formed by rules we have not fully written. These are not the sounds of a science falling apart. They are the sounds of a science standing right at the threshold of its next great idea, close enough to feel the draft coming through the cracks. This has happened before, every single time. Newton's gravity was a magnificent first draft that ran the heavens for 2 centuries, until tiny cracks appeared, a slight wobble in the orbit of Mercury that would not fit, and those cracks did not destroy physics. They opened the door to Einstein, to a picture of gravity as the curving of space-time itself, deeper and stranger and more beautiful than anything Newton imagined. The cracks in the old physics of the atom did not end science. They gave us quantum mechanics. Every time our best theory has started to disagree with itself at the fine edges, it has been standing on the doorstep of a deeper theory, and the disagreement was the doorway. And consider how much better positioned we are, in a sense, than the physicists who came before us. When the cracks appeared in the old physics of Mercury's orbit, there was essentially one crack, one small anomaly, and it took a mind like Einstein's to see the whole new world hidden inside it. We have not one crack, but many, all at once, all pointing, all pulling, in ways we are only beginning to map. That could feel like the situation is worse, but I would ask you to see it the other way. More cracks means more clues. More independent anomalies means more constraints on what the deeper theory must look like. More arrows converging, from more directions, on the same hidden truth. The universe is not being coy with us. It is being generous. It is handing us puzzle piece after puzzle piece, in the Hubble tension and the dark sector, and the early galaxies and the ancient light, and somewhere in the way those pieces fit together is the shape of the next cosmology. We may not be clever enough yet to assemble them, but we have never had so many pieces on the table at once. I think, too, about what this means for the ordinary experience of being alive and curious. It is tempting to imagine that all the great revolutions in understanding happened safely in the past, that the heroic age of discovery is behind us, that we live in the tidy afterward, where everything important is basically known and only the details remain. What tonight should tell you is that this is simply false. We are living inside an unfinished story. The textbook account of the origin of everything, the one printed with such confidence, is being quietly rewritten around us, in real time, by telescopes and surveys running right now, tonight, while you lie there in the dark. The next Einstein may already be alive. The idea that will resolve the Hubble tension, or explain the dark sector, or reveal what the singularity truly hides, may be forming in some mind at this very moment, or may be waiting for a mind not yet born. And you are here for the part before the answer, the part where the questions are sharpest and the mystery is most open, which is, if you think about it, the most romantic chapter of the whole story to be present for. And that is why I do not want you to feel fear tonight, lying there in the dark. I want you to feel something closer to privilege, because to be alive at exactly this moment, when a paradigm is straining, when we can see the cracks clearly and do not yet know what will grow through them, is one of the rarest and most exciting positions a curious mind can ever occupy. The people who lived in the last years before relativity, in the last years before quantum mechanics, stood exactly where you are standing now, at the edge of a settled picture that was quietly coming apart, on the verge of a revolution they could feel but not yet name. We are standing in that same narrow, electric gap, the gap between one story of the universe and the next one, the place where the next cosmology will be born. So the next time you hear that the more we study the Big Bang, the less sense it makes, I hope you will hear it the way I have come to hear it. Not as a theory failing, as a universe, patient and vast, and stranger than any story we have told about it, leaning close and telling us, in the only language it has, in disagreeing numbers and missing ingredients and a beginning it will not show us, that our first draft was only ever a first draft, and that the real story, the one we have not written yet, is going to be more astonishing than anything we currently believe. The universe is not making less sense. It is quietly, patiently, getting ready to make a deeper kind of sense than we have ever known, and we get to be here, awake in the dark, at the very moment it begins.